let's have a look at how Hypernetworks can help with the limitation of current neural texture compression. So just to give you a little motivation of why we are looking at neural texture compression, here is a report from TechSpot which analyzes the footprint required by games by date of release. And as you can see, all games or modern games are not getting smaller and smaller, it's quite the opposite. And if we try to analyze who's the culprit here, what is increasing and what is causing us damage, we can see here in this kind of analysis of Call of Duty Modern Warfare package that more than 50% of the game package is actually images. And when we talked about images, actually, so we need to find a way to reduce the storage to actually be able to compress better the games. And the culprit here is physically based shading, actually. So as a community, we have created a problem by just creating more and more refined BRDF model. I played culprit here, but we need to find a way to actually cope with that. Why so? Because physically based shading actually requires many texture per material. So you don't really, by adding new features to the physically based shading standards, we are also adding all the parameters that we need to have to input, for example, the diffuse, the normal map, the metalness, the roughness, and so on and so forth, just for one asset. So our goal here is to reduce the storage of all the texture that comprise and are used for a single asset into a much more compressed format. And the idea of neural texture compression is that maybe neural method can help. So to understand why they can help, we have to look at the traditional way of compressing texture. And usually what we do is we group parameters together when they are meaningful, and we compress them by using, for example, RGB or HBA texture, and we compress them separately. For example, we compress the normal map. You see a BC method, which is compatible with the hardware acceleration of the texture unit, the albedo as well. And doing so, we are missing something, which is the correlation between some of the layer. That means some of the parameters, they are highly correlated, and maybe we can use that to compress even better. And so the question is, why don't we compress all the texture set at once into one single representation like this? And this is where enters neural texture compression. And the way it works is the follow, you take your texture sets, which is a set of different textures for different parameters, and you use a gradient descent algorithm to optimize both a small set of texture, which is called the latent textures, and a set of weight and biases that are used by a multilayer perceptron to actually decode the latent images into the target texture. And these structure is the bare bone of all the neural texture compression methods that exist today, from NVIDIA NTC to Ubisoft BCF, AMD TBC, or Intel TSMC. But using stochastic gradient descent has some limitation. And the first thing it does, it requires you to fix some of the formalism before the optimization. You have to fix the neural network you're using, you have to fix the form of the latent representation you're using, and etc. The other requirement is that you need a lot of iteration of your stochastic gradient descent to actually converge to something that is of reasonable good quality. Usually people go towards 40K iteration, which is large, and it can be slow. So here is an example of an optimizer running. It will update the window every 100 iteration, and you can see it's starting to come together. We can see the structure coming to appear here, but it is taking some time. And at this point, you wish you had a better GPU, like maybe Chris can give us some like 5080 so that it runs faster, or maybe we can find a solution to that. And so the solution we would like to have is you take this kind of like offline process where internal process where you just provide your texture sets as inputs. You press the compress button, and in a few seconds you have your texture set compressed. And that is that will be much more appreciable, and probably the artists would like to use it instead of waiting hours to compress all the game's assets they are producing. So how do we get rid of the gradient descent algorithm? So let's go back to the picture, and we are going to be not clever at all. We replace the gradient descent by a neural network. Yeah, I mean, it's nowadays way to do things, right? And such a neural network is actually called a hypernetwork. I didn't take the name. It's the neural network community who's responsible for it, but that's what it's called. The good point of having a neural network that just compresses your input textures into the latent representation weights and biases, it's very fast to compress. It's also scalable as long as your neural network is linear in complexity. It's also flexible because you can then use your neural network to actually do other things. And it's even more flexible that you can repurpose the API networks for other tasks. And I'm going to show you a couple of examples of other tasks in the presentation. So, but first, let's have a look at how is the hypernetwork structured. And this is an overview of the architecture. It's not something very clever as well. I mean, it's quite a standard things, but there are subtleties here and there that needs to be tackled. So in input, it takes the texture set as a free tensor. Well, 40 if you have the batch size, but let's not take care of it right now. And it will modify or actually generate internally 2 sets of tokens as 2D tensors. The first token is the T1 you see here on the screen on the left, and it's responsible to actually modeling the MLP weights and bias. And the other tensor set of tokens is actually trying to reproduce the latent texture. And as output, we need to output the weight and bias as well as latent space. And why do we need a transformer architecture? Because this is a transformer architecture. We needed that because we found it's way better than UNet of convex for equal size. And the insight behind it is that side scaling, which you would need to use if you were using UNet or convex, is not very good actually at sharing information between 2 latent representation, and cross-attention is way better. So this is why a transformer architecture is very handy in this configuration. But a transformer architecture requires you to tokenize the input and output. And this is the 2 first block you see in the graph here. The first one I'm not going to talk about is one very similar to what Vision Transformer do, and it's the white one. It just do a patch of 4x4 texels and group them together to form a latent code. The one that is custom to our architecture is the T-encoder you see here, and it's necessary to generate the token for the MLP. So how is it structured? It's a series of convolution and cross-attention blocks where we start from a frozen T0 latent code, and we update it by doing cross-attention with the input texture set so that it gathers information from the texture set at different resolution. Once we have that, we have our T tokens, and we need now to update the X token, which are responsible for the latent. And to keep the computation linear, we use cross-attention. So we have something that will scale, and we avoid the quadratic cost of self-attention. There's something to notice here is I'm using peri-normalization, which is basically doing layer normalization sandwiched between the different elements, and that is very efficient to actually provide for the gradient flow. Okay, and now with this block we are updating only the X token, so the remaining T token is actually doing a pass-through until the end. The last block is you need to convert this X token into a set of latent textures, and that is this BC1 conversion block, which basically turns that into the NTC representation you're using. For example, here we are using the TSNC format we presented with Ernest last year at HPG, and so you need to have a form that is compatible with BC texture format. Okay, so to train the hypernetwork, you first need a data set, and for that I collected a lot of texture from Polyhaven, Sketchfab. In total, there are more than 2,000 unique texture sets at 4K resolution, and those textures are used to train the hypernetwork using random transformation, both in rotation scales, but also changing the hue, saturation, and lightness of the diffuse component, as well as nonlinear transformation for elements that can apply to, for example, we don't change the normal map because there's no real transformation that preserves what the normal map is. And then we use random image size during batching to train the neural network to be robust against different resolution size. And the rest of it is very, very straightforward. It's just Adam with weight decay and a constant learning rate. The loss is just a blend with equal weights of L1 and perceptual loss, and it's trained on a single GPU, so you don't need a very big cluster for that as well, so that's fine, and with a reasonable number of iteration. So here's the results. So you have the reference, the input to the hypernetworks on the left, and on the right, it's the output after decompression by the NLP. And you can maybe spot a few differences, but overall, the quality is quite good. And if we look at the results after rendering, once all the maps of the texture set are used, it's pretty close in terms of rendering. In terms of metrics, so the output of the hypernetwork is not exactly as good in terms of PSNR to using the Stochastic gradient descent with 40K iteration from our last year model. But on the other side, if you look at the MSSSEM, it's much better. And the reason is that we incorporate a perceptual loss in the training of the network, which is not used to train NTC models. So I will try to do a little demo here to just show you that it actually is running fast. So I have my computer at the office, which is running the same GPU that was used to record the video of the optimization process. And if I hit compress, in a few seconds, we'll have it. Yeah. Okay, so now we can think of other things we can do with the hypernetwork. And the first one thing that I tried is to actually output a single set of weight and biases for all the texture set the hypernetwork can generate. And for that, there's a simple architecture change. You just remove the encoder, the T encoder, which converts to tokens. So you just have the T0 token that I referred to previously. So now all the assets share the same MLP tokens. And what happens is you decrease a bit the quality. Actually, not that much, but there's a decrease in quality. But the gain you have is that now, when you do the evaluation in screen space of your neural networks, all the evaluation use the same neural network, so all the assets use the same neural network, and all the sorting and caveats you have when you were using, for example, cooperative matrices or cooperative vectors, you don't have to care about it anymore, and so the result is much faster. Now, what we can do as well is alleviate the restriction of having to work with a specific set of configuration for the TSNC that was used for SGD. We can output different MLP version very easily by just adding different heads to our neural network at the end. So, for example, if we want to change the size of the hidden layer from 16 to 64, for example, we just have to add a few outputs here, and that can also be done afterwards by just training or fine-tuning from a frozen architecture. Now, one thing that I thought very cool was to actually use the hypernetwork to learn texture upscaling, which the SGD cannot do. And for that, what you change is you change the loss of this network. You put as input the MIP1 of your texture set, and in the loss, you replace the MIP1 of the texture set, the reference texture set, by the MIP0. And what it does is it forces the multilayer perceptron to learn to do texture upscaling. So when you look at this is a crop from the inputs that is provided to the hypernetwork, and what the MLP is actually evaluating in the end is this. And notice that the MLP has never been trained on an higher resolution thing. It's completely hallucinating. So this is done for my presentation, and if you're interested into more details, there's the paper available on arXiv, the code for the hypernetwork on GitHub, and there are weights in this Hugging Face page. Thank you.
So there is indeed time for questions. There's one over here.
Hi, thanks for the amazing talk. I wanted to ask what kind of perceptual losses you incorporate.
It's DISTS.
Okay, so do you use this only for the albedo? Have you seen any kind of like performance degradations if you use it across other things like normal maps? Because perception metrics are usually computed on naturalistic images, right? So normal maps are very far from what we call naturalistic in a human vision sense. So
it's funny because the perceptual loss are actually very good for other tasks. And what I'm using is I'm actually using a specific way to do the loss, in which you take random channels from the texture set, the output texture set, and you apply the perceptual loss on it. It has been proven, in our team, that it works very well.
Have you also applied it with LPIPs or any other visual difference predictors?
So you mean trying other kind of losses?
Yeah.
Yeah, so I tried also to put SSEM. Didn't change much. So I guess just having a perceptual loss. So having a perceptual loss really made a difference in terms of visual artifacts. You get way less block artifacts that you could have because the internal representation is a BC1 texture, which is block compressed, so it has blocks. And if you have a perceptual metric, it just removes a lot of those blocks artifacts, whatever the perceptual metric I trained on.
And you're using a weighted sum for the loss, or just a summation?
Summation.
Okay, thanks.
There would be time for a further question, which we have over here.
Thank you for the presentation. So comparing with this hypernetwork with the original neural textures, is this behavior quality loss constant, or you see some edge cases that this hypernetwork doesn't perform well?
So there are edge cases where the hypernetwork is less efficient than having a stochastic gradient descent, is when you have very brutal color variations. It can happen that also the stochastic gradient descent method misses some color information because of the bootstrap of the gradient descent that happens. And it turns out that sometimes the hypernetwork also lacks. It's not in the same places, but it lacks the ability to actually fully gauze and represent all the colors that are in the texture set, but that's probably more due to the fact that having a small MLP to represent a very wide histogram is not ideal.
Makes sense. Thank you.
Thank you for the presentation. I was just wondering, do you think it would be feasible or still helpful to adapt these neural texture compression methods to do lossless compression, like bit exact compression, and how much? So I see that you don't optimize for the compression ratio, but that still works. So how feasible would it be to do lossless with this type of neural methods?
So I have no idea. I don't know how you would manage to get something that's lossless. I mean, apart from storing the residual, but then, I mean, you might lose a lot of compression ratio doing so it might be difficult.
Yeah,
I don't know. So just say, it would be interesting, but it might just completely degrade the purpose of having a neural network.
Yes, thank you.
Is it a quick question? Go for it.
You predict a very small MLP. Could you use like a second order optimizer to train that MLP instead of this hypernetwork?
So can we add, like, for example, gradient descent on the MLP that's outputted by the hypernetwork?
Can you get rid of the hypernetwork and use second order instead of SGD, like a Levenberg markup or something? As in, instead of training using SGD, you train using a second order method, which is typically much faster, because you have so few parameters that you might.
So you could, but the problem is the starting point.
I see.
And the MLP starting point, you cannot predict a good starting point of the MLP, and that is why you need so many iterations, because the starting point is just crap. Really, it's crap.
Okay. Interesting.
Meta learning would give you the starting point, I heard.
Okay, thank you.
I don't think we have further time for further discussion, but thanks for all the questions to all the papers in this session. Remember what Romain said, don't run away, there's a picture going to be taken, and let's thank all the speakers again.